Hello, everyone at Cosmology from Home. My name is Taylor Hoyt. I'm a PhD student at the University of Chicago, set to defend in just a few weeks. Today, I'll be talking about my work into recalibrating the tip of the red giant branch distance scale and the implications of that work on measurements of the Hubble constant. Before I go on, I want to highlight a few of my closest collaborators over the past 6 years while I pursued my PhD. This includes Insung Jang, Violet Major, Mark Siebert, Rachel Beaton, Barry Medor, and of course, my PhD advisor, Wendy Friedman. I think we've done some really great work together and really pushed the field forward. So briefly, I will provide context and a brief summary of the tip of the red giant branch. Then I will present on my recent comprehensive study of the TRGB and the Magellanic Clouds. Then I will cover a new calibration of the TRGB based on the megamaser host galaxy NGC 4258. This study uses brand new high signal-to-noise data from the Hubble Space Telescope as part of my Cycle 29 program. Finally, I will briefly discuss the literature on TRGB calibration and conclude with a look to the future of Hubble constant experiments. So briefly, to summarize the cosmological context and the Hubble tension, here I'm showing a compilation of extensions to LCDM that are designed to bridge the gap between the CMB and the Cepheid-derived measurements of H0. Shown on the left are what are called early dark energy extensions to LCDM, and on the right are late dark energy extensions to LCDM. What can be seen here is that it's not easy to bring the Planck value of H0 into agreement with the Cepheid value through LCDM extensions alone. However, I think it is illuminating to consider where the CCHP's TRGB constraint on H0 lands in this plot. As you can see with the red band here now, which represents the TRGB, in between Planck and Cepheids, it's much easier to bridge the gap, if there is one, between the Planck and TRGB H0 values. And this brings me to a point that I really want to leave everyone with, and that is to think beyond claims of 4, 5, 6 sigma evidence for the Hubble tension, and to instead focus on reaching the most accurate constraint on H0 that theorists can then use to rule out sections of model space. And we can all approach a more complete understanding of the universe. So now I want to briefly get into what the tip of the red giant branch is and what exactly we're measuring. So what I'm showing on the left is the astronomer's favorite diagram called the Hertzsprung-Russell diagram, which displays the brightness or luminosity of stars as a function of their temperature, or as we measure it as the color index. So I'm showing here what's called the main sequence, which is where all stars spend the majority of their lives. And I've shown as a white dot where a sun-like star would exist. We're going to follow that sun-like star to the end, near the end of its lifetime on the red giant branch. So the sun, as we're seeing it, has finished burning hydrogen in its core, and it now has an inert helium core. This core continues to shrink, and the temperature increases in a shell around the core until hydrogen burning can resume in this thin shell surrounding the core. The core continues to contract, becomes more degenerate, and the star expands. More energy and more helium ash is deposited into this core, which is also, of course, degenerate. So once the temperature to burn helium is reached, we hit, of course, a thermonuclear runaway because there's no pressure valve to relieve the increase in temperature. However, the energy production in this thermonuclear runaway is so high that in just a few seconds, degeneracy is lifted, stable core burning of helium is established, and as we saw, there's a rapid evolution off the tip of the red giant branch when this non-degenerate helium core burning is established. And so the key here is the evolution from the red giant branch to these regions is extremely rapid. And we observe this truncation in the counts of RGB stars and stellar populations at a standard luminosity. And it turns out that the luminosity at this tip of the red giant branch is a constant or invariant when you look at old metal poor red giant stars. So observing the TRGB in actual data, this is an empirical a representation of the HR diagram I just showed in the last slide at the commonly used wavelengths to observe the TRGB as a standard candle. Without getting too much into it, it just so turns out that these wavelengths are the perfect energies at which to observe the TRGB as a near perfect standard candle. So you can see here this kind of flat truncation of counts in the red giant branch, which is due to that, of course, rapid evolution off of the tip of the RGB that we just looked at prior. And so looking at some more examples of dwarf galaxies in the nearby universe, which are dominated by older, less massive stellar populations, which I was mentioning are the necessary components to establish the TRGB as a distance indicator. And so to accomplish this in the much more massive galaxies that host supernovae 1A, we need to target their ancient stellar halo populations. And this is what the Carnegie Chicago Hubble Program did, and first results published in 2019 and an update in 2021. So in terms of calibrating the TRGB, what options do we have? And when I say calibrating, I mean calibrating the intrinsic brightness of the TRGB luminosity so that we can then use it as a gauge of distance. There are three main avenues, and that is one, the Magellanic Clouds. There's also indice 4258. Lastly, there is also the option of parallaxes in the Milky Way. However, Gaia DR3 isn't quite at the level of accuracy in their parallax 0 point needed to compete with, for example, the special eclipsing binaries and the LMC calibration. And I just want to emphasize that all astrophysical distance indicators, Cepheids, TRGB, Miras, JAGB, SBFs, Tully-Fisher, supernovae, all have their 0 point set by some combination of these few geometric calibrations. And so when you see these kind of plots, these useful compilation plots of all the various H0 measurements, many of these points in these kind of compilation plots are covariant. They share in common over half of their variance. And so keep that in mind whenever you're interpreting those plots. So now I'll start with my own work in calibrating the TRGB in the Large Magellanic Cloud. So the Magellanic Clouds are, of course, our beautiful neighbors in the southern sky, observable in the southern sky of Earth. And you can see them here relative to the Milky Way disk in the bottom right in this beautiful image produced by Gaia. And zooming in a bit further, we can see the extent of the Magellanic Clouds, the large Magellanic Cloud on the left and the small one on the right, the moon disk for comparison. The TRGB calibration in the Magellanic Clouds has received a lot of attention in the last few years, especially after we published our first results from the CCHP. Basically, the sole topic of discussion has covered dust extinction along LMC sightlines. However, it's very important to note that even after subtracting out all differences in assumptions made about the dust reddening, there is still a residual 8% discrepancy between the SHU's and CCHP's proposed values for the apparent brightness of the TRGB and the LMC. That means from measurements alone, using the same flux measurements of the RGB stars, normalizing over assumptions of the dust reddening and assumptions of the distance of the LMC, there's an 8% disagreement in just measuring where that truncation lies in the HR diagram. There's a similar discrepancy in the small Magellanic Cloud. So in this paper, I hope to address that and solve this problem and once and for all get the calibration in the Magellanic Clouds that we know is possible because of the properties of their stellar population. And so the main results of that are shown here, where I plot the observed TRGB brightness versus the TRGB statistical uncertainty determined from bootstrap experiments. And I've colored each point on this plot according to the relative fraction of younger stars that exist in that spatial bin of the LMC, which is determined from an external map of the star formation in the Large Magellanic Cloud. And what you can see is that there's a clear three-way correlation in that the more uncertain the TRGB is, as probed through the bootstrap simulations, the more biased the TRGB brightness is to fainter values. And this is also then correlated with the relative proportion of young stars in those fields, which is all consistent with our understanding of the TRGB not being a standard candle in young populations of stars. So improving the sample selection to exclude these imprecise TRGB features from consideration, I come to the final measurements, which I show on the left here, or in the top left, which is the nominal sample where the star-forming imprecise regions have been excluded from consideration. And for comparison, I've shown the inverse of that selection to show how messy and noisy the imprecise fields are and how they produce a very useless color magnitude diagram for the tip of the red giant branch because it's not a standard candle in those regions. And then for comparison, I brought back those 8 prototypical fields from the earlier slides. So you can see just how well the calibrating CMD in the top left resembles these ideal measurements of the nearby dwarf galaxies. And so a number of powerful consistency checks came about through this paper. Together, these consistency checks span multiple astrophysical probes and both clouds. They reflect an understanding of the true distance, reddening, and multi-wavelength TRGB magnitudes across the Magellanic system to better than 2% in cumulative accuracy. That is, if one of these components of this cross comparison was shifted, say the TRGB calibration to match what the Shoes team advocates for the TRGB 0 point, then the other two would become completely inconsistent with the TRGB. So there's no room to shift the TRGB 0 point by any more than 2% in total. So now moving forward, since there doesn't seem to be much more debate over what the TRGB 0 point should be, I've begun moving forward to improving our precision and accuracy and just improving our constraint on H0. And this leads me to a new paper that I'm working on using my new Hubble Space Telescope program on a legacy calibration of the tip of the red giant branch as constrained by HST. Very briefly, I want to go through recent attempted calibrations of the TRGB in this same galaxy. So Reed et al. 2019 proposed a measurement based in the star-forming disk of NGC 4258, which some of us showed in a later paper you really can't do. So Zhang et al. Targeted the actual stellar halo of NGC 4258, same as the CCHP did in the supernova hosts, and found that within this region I've drawn here, the stellar population is too disk dominated to measure the TRGB accurately. And this is exactly what a recent paper from Anand et al., so the Cosmic Flows Tully et al. Group collaborated with Shoes, Rees et al. They claimed that their data were located in the stellar halo according to the definition of Zhang et al., which is not the case as shown here. And they also changed their 0 point calibration using these new data, which are actually of lower quality than their original calibration. So it's unclear why they made this shift, but as we'll see in a second, we can do much better than that. So what I've just plotted up here in the white fields are where my new data are taken in the stellar halo of NGC 4258. So importantly, it avoids all H1 emission, which is a tracer of dust, which the recent Anand 2021 fields suffer from severely. It'll also be at 2.5 times higher signal to noise than these recent studies. And through aerial coverage and signal to noise will reach the systematic floor of the maser distance. Just to compare really briefly, an important aspect of minimizing systematic uncertainties is matching exactly the environment and observing conditions of your calibrator to the host galaxies that you're applying a calibrated method to. So we're calibrating 4058 to measure TRGB distances to some of these supernova hosts in our H0 paper. And so you can see that the new field selection mimics the halo selection of the supernova host sample, which gives a perfect like-for-like comparison, which is necessary to reduce systematics in the cosmic distance ladder. So now I'll briefly show some preliminary results from 2 of the fields in the halo of NGC 4258, shown here on the left and the right. The 2 results are consistent with each other, well within the uncertainties, and combined give a calibration of the TRGB of about -4.045, which is fully consistent with the Friedman 2019, 2020, Zhang 2021, Hoyt 21 calibrations of the TRGB, and the long-term calibration of the TRGB as well. So briefly comparing now the color magnitude diagram to the supernova hosts, you can see that the calibrating 4058 data on the right match really well our highest signal to noise imaging of M101 in the CCHP sample. the color magnitude diagram looks almost identical with a clear RGB luminosity function and a clear peak in the edge detector response function, which is just, you can think of as a first derivative kernel passed over the counts of RGB stars. So it finds the point of sharpest discontinuity. So now I want to get into the final, how well can we do with these new papers that I've introduced? So on the left here is the Friedman 2019-2020 calibration of H0 and the uncertainty there. And then here I show the calibration uncertainty of the TRGB from the Hoyt 21 paper and the LMC and the in-prep paper of NGC 4258. And in the right column, I note the combined uncertainty. So in the end, I've almost cut the calibration uncertainty in half with these new data and analyses in the geometric calibrator stage of the TRGB. And it's purely from improving the measurement of the TRGB. How well can we measure the TRGB and can we do better? And the answer was yes. So the effect on the total H0 error budget. So this talk, the TRGB calibration reduces to 1.2%. So in total H0, that's a reduction to about from 2.7 to 2.2%. And going forward, how can we do better? Even if we double the number of TRGB distances to supernova host galaxies, we get to 1.8% in total H0. For reference, Planck is about 0.8%. So it's clear that we are hitting diminishing returns of the standard approach of photometric supernovae. So we need a method that provides more statistical weight per supernova 1A than the photometric Phillips trip relations. And spectroscopic standardization of supernovae could provide such a path forward. And here are my summary conclusions. Thank you for your time.